The third video in our mole unit is really an extension of the second video. We'll still be dealing with the molar mass of substances. This time we'll be talking about the molar mass of compounds. So the learning targets are actually exactly the same as we just had for the last video. Do note this time we will be learning how to calculate the molar mass of compounds. In fact, that's the first thing we'll be doing here. So I want you to consider this. If we have 1 mole of water, that 1 mole of water would contain 2 moles of hydrogen atoms, and the reason I know that is the subscript 2 is next to the hydrogen, and 1 mole of oxygen atoms. So if I want to calculate the mass of 1 mole of water, in other words, if I want to find the molar mass of water, I need to find the mass of 2 moles of hydrogen and add that to the mass of 1 mole of oxygen. So thinking about our mass, or our moles to mass conversions that we learned about in the last video, 2 moles of hydrogen times the molar mass of hydrogen, which just look that up in the periodic table, 1.01 grams per mole. There would be 2.02 grams of hydrogen in every mole of water. And then 1 mole of oxygen has a mass of 16 grams, so there would be 16 grams of oxygen, 1 mole of water. So the molar mass of water is simply the sum of those two, the 2.02 grams plus the 16 grams. That gives us 18.02 grams. So the moral of the story here is that the molar mass of any compound is simply equal to the sum of the molar masses of each element in the compound, factoring in how many moles we have. In this case, 2 moles of hydrogen, so we have to multiply the molar mass of hydrogen by 2. So let's look at some examples of how we go about calculating this. I'm just asked you to calculate the molar mass of each compound. As we go through this, you definitely want your periodic table out. You want your calculator. Do the calculations right along with me. Make sure you're plugging in to your calculator exactly as you see it here. That will help you learn how to do this. This is something that you never want to mess up because it's a basic calculation that you'll need to do. So, for example, we're asked to calculate the molar mass of each compound. We have SO2 to start with. Find the molar masses of those elements on the periodic table, sulfur and oxygen. Notice in the formula, if I have 1 mole of SO2, there'd be 1 mole of sulfur and 2 moles of oxygen. So here's what we plug into our calculator. 1, or you wouldn't even have to hit 1, times 32.07, because that's the molar mass of sulfur, there's 1 mole of it, plus 2 times 16, because every mole of oxygen has a mass of 16 grams. And when you plug this in your calculator, you don't even need to use parentheses. Your calculator does the order of operations correctly. So in this case, if you simply hit 32.07 plus 2 times 16, no parentheses necessary, it will give you 64.07. That's exactly what it will tell you. So 1 mole of sulfur dioxide, or SO2, has a mass of 64.07 grams. Let's look at another one. This is barium hydroxide. So look at the formula, ask yourself, how many moles of each element are in 1 mole of the compound? Well, looking at the formula here, I can see there's 1 mole of barium. And then remember the parentheses apply to everything inside the parentheses applies to the subscript. So there's 2 moles of oxygen and there's 2 moles of hydrogen in here. So when I plug this in my calculator, 1 times 137.33, or just 137.33, because that's the molar mass of barium, plus 2 times the molar mass of oxygen, which is 16, plus 2 times the molar mass of hydrogen, which is 1.01. That gives you 171.35. Next example. This is iron 3 sulfate. So again, ask yourself how many moles of each element are in the compound. From the formula, I can see there's 2 moles of iron. And again, remember with the parentheses, the subscript 3 applies to everything inside the parentheses. So there are 3 moles of sulfur, and there are 12 moles of oxygen, because 3 times 4 would be 12. So when I plug this in my calculator, 2 times the molar mass of iron, 55.85, plus 3 times the molar mass of sulfur, which is 32.07, plus 12 times the molar mass of oxygen, which is 16, should give you 399.91. Now, one thing to note here on these calculations is yes, even though we are hitting the multiplication button, the sig figs actually follow addition rules. And the reason why that is simple. There are exactly, going back to our first example here, 2 moles of oxygen in every mole of SO2. There are exactly 12 moles of oxygen in every mole of the iron 3 sulfate. So when we hit 12 times 16, for example, on this last problem, what we're really doing is we're taking 16 plus 16 plus 16, etc., 12 times. It is exactly 12. There's no measurement there. And so when you get your answer here, you simply look at the decimal places. And the periodic tables that you all have all go to 2 decimal places. So this should make it very easy for you. Molar masses that you calculate will always have 2 decimal places in them. Simple as that. So it should make it pretty easy for you. All right, continuing with the same thing here, go ahead and try this on your own. Okay, so pause the video as each substance comes up, get the molar mass, and then see if you did it correctly. All right, so we have fluorine here. You might be thinking, well, that's just an element. I just look it up. It says 19. Well, but remember, as we've learned in class already, fluorine is a diatomic element. When we talk about fluorine, we're not just talking about fluorine atoms. We're talking about fluorine molecules where there are 2 atoms of fluorine in that molecule. So the molar mass of fluorine would be 2 times that, so 2 times 19, or 38 grams would be the molar mass of fluorine. All right, next one, xenon heptafluoride. Again, ask yourself, how many moles of each element are there? Well, I can see there's 1 mole of xenon, 6 moles of fluorine. So the molar mass of xenon is 131.29. Adding that to 6 times the molar mass of fluorine, that should give you 245.29. All right, last example here. We have iron 3 nitrate. Again, ask yourself, how many moles of each element are there? We have 1 mole of iron, there are 3 moles of nitrogen, and there are 9 moles of oxygen. So the molar mass of iron plus 3 times the molar mass of nitrogen plus 9 times the molar mass of oxygen gives you 241.88 grams. So we've looked at how we calculate the molar mass of compounds. That calculation in and of itself really is not the goal of anything. The reason why we have to do that is we have to be able to use those molar masses in other calculations. There will never be a problem where you're simply asked, maybe outside of the homework you're going to be doing just to practice it, but there will never be a problem where you're simply asked, calculate the molar mass of this, because that's really not the purpose of doing it. We need to use it in other calculations. In other words, we need to be able to do this learning target number 6 here. Use these molar masses to convert between moles and mass of a substance. So we looked at examples of this in the last video when we dealt with elements. Nothing is different about how these problems are worked, except for the fact that we now have to calculate the molar masses first. So let's look at an example. We were asked, calculate the mass of 0.73 moles of calcium chloride, or the formula CaCl2. So this is just like the problems we were doing in the last video. We're converting from mass to moles, so we need to use a molar mass. One thing I'd also encourage you to do during this video, if you haven't printed it out yet, print out the slide from the last video that has the flow chart on it of moles, mass, particles. That will be very helpful to you here. You can follow along on these problems to see how those flow charts work. So in this case, we're given a number of moles and asked to find a mass. And if you look at that flow chart, you can see we need a molar mass. Well, the difference between what we're doing here and the last video is we have to calculate this molar mass of calcium chloride. It's a compound. We can't just look it up on the periodic table. Now, as far as I'm concerned, you don't really need to show me your work for the calculation of the molar mass. I know that's very different than what I usually tell you. This is one of the few exceptions where I don't really need to see it. However, if you want to show it, calculating your molar mass of calcium chloride, go ahead and do that if that helps you. So it would look something like this. We have 1 mole of calcium, so just the molar mass of calcium, 40.08 grams, and then 2 moles of chlorine, so 2 times 35.45, that gives you 110.98. That mass we will need to use in our problem. So we're starting with the 0.73 moles of calcium chloride. We need to convert it to a mass. So this is where we use this molar mass we just calculated. Thinking about what a molar mass is, that is the mass of 1 mole. So I can use that as a conversion factor. 1 mole of calcium chloride, which goes in the denominator, would have a mass of 110.98 grams of calcium chloride. Notice your moles cancel. We're left with grams. We've done the problem. You plug it in your calculator, and you get 81 grams. Notice here 2 sig figs, because our initial number of moles had 2 sig figs. All right, next problem. Go ahead and try this one on your own. So a lab calls for 1.15 moles of potassium iodate, that'd be the KiO3. What mass in grams of KiO3 will you need? Notice this is the same problem we just had. It's a moles to mass conversion. So we need to find the molar mass of KiO3. So you want to calculate that. So we have 1 mole of potassium, we have 1 mole of iodine, and 3 moles of oxygen. Should give you 214.00 grams for your molar mass. So converting from moles to mass, again we just use our molar mass as a conversion factor. Every mole of potassium iodate has a mass of 214 grams, so moles cancel, and we get 246 grams of KiO3. Next question. Convert 18.5 grams of aluminum hydroxide to moles of aluminum hydroxide. Notice this question is the reverse of the previous two. We're still dealing with mass and moles in our conversion. Now this time it's the other way around. We're going from mass to moles instead of moles to mass. But we're still going to use the molar mass. We still need to calculate it. Also notice in this problem, unlike the first two, I don't give you the formula of the compound. This will usually not happen, but knowing now that you know the nomenclature, or hopefully we should know it, you should be able to figure that out. So the formula for aluminum hydroxide is AlOH3. So we need to find the molar mass of that, which ends up being 78.01 grams. Now as far as the problem is worked, we're starting with a mass, so our molar mass needs to go in the denominator of our conversion factor. So notice that 78.01 grams goes in the denominator. So grams of aluminum hydroxide cancel. We're left with moles as we set out to find, and that should give you 0.237 moles of aluminum hydroxide. Try this one on your own. We're told in a lab you use 0.7500 milligrams of magnesium chloride, MgCl2. How many moles is this? Well, this is essentially the same question we just saw. It's a mass to moles conversion, so we need the molar mass. Now, do note here, the mass this time is given to us in milligrams. So we're going to have to deal with that in our problem. You still need to calculate the molar mass of magnesium chloride. Notice we have 1 mole of magnesium and 2 moles of chlorine. Should give you 95.21 grams. The important point here, as far as the milligrams is concerned, is you need to convert that into grams because your molar mass is in grams per mole, not milligrams per mole. So milligrams to grams, there are 1,000 milligrams in a gram, so there's your conversion factor. So milligrams of MgCl2 would cancel, leaving us with grams of MgCl2. Now we can use this molar mass that we calculated here. So we can see the molar mass goes in the denominator where grams of MgCl2 will cancel. Plug it in your calculator and you should get 7.877 times 10 to the negative 6th moles of magnesium chloride. Next example. Determine the mass of 4.87 times 10 to the 21st oxygen molecules. So notice in this problem, we're not given moles. We're given a number of particles. So if you look at your flow chart here, this will involve two conversions. We're going from particles to mass, so we need both Avogadro's number and the molar mass in order to do this conversion. So we will need to find the molar mass of oxygen. Again, remember oxygen is diatomic, so it would be 2 times the molar mass of oxygen, or 32 grams per mole. So as far as the problem has worked, we'll start with what we're given, the 4.87 times 10 to the 21st oxygen molecules. I need to convert that to moles first. I can't go straight from moles or from molecules to grams because I don't know the mass of a single molecule of oxygen. So here's where we use Avogadro's number. Remember, 1 mole of anything is Avogadro's number of those things. So 1 mole of O2 would be 6.022 times 10 to the 23rd molecules of O2. So molecules of O2 would cancel. Now we can use that molar mass of oxygen. 1 mole of O2 has a mass of 32.00 grams. And moles of O2 cancel. And we get our mass of 0.259 grams of O2. Try this one on your own. Determine the number of molecules in 7.55 grams of propane. And I give you the formula there, C3H8. So notice this one is the reverse of the one we just did. Here we're asked to find particles and we're given mass. Before we were asked to find mass, we were given particles. So again, you will need both Avogadro's number and molar mass. You need two conversion factors here. So the molar mass of propane we need to calculate. Notice there are 3 moles of carbon and 8 moles of hydrogen. So 3 times the molar mass of carbon plus 8 times the molar mass of hydrogen gives you 44.11 grams per mole. So as far as doing the calculation here, starting with the mass we're given, 7.55 grams of propane, we can use our molar mass to convert that into moles. Notice your molar mass needs to go in the denominator here. So grams cancel. And then we're left with moles. Now we can convert from moles to molecules. We know every mole contains Avogadro's number of particles. So there are 6.022 times 10 to the 23rd molecules of propane in every mole of propane. And we're left with molecules, and we get 1.03 times 10 to the 23rd molecules of propane. All right, last problem here. How many sulfate ions are in 1 gram of iron 3 sulfate, or Fe2SO43? Before we even look at the work in the problem here, just consider the question. We're asked to find a certain number of particles within a larger particle. The sulfate ion, formula SO4, is within this larger particle. So this is a scenario where we have 3 conversion factors. If you look at those flow charts, you can see we can go from mass to moles to particles. And then once we're in particles, we can go to particles within particles. So we'll actually need 3 conversions here. We will need Avogadro's number. We will need the molar mass, just like we saw in the last couple of examples. But we'll also need to use the formula, this Fe2SO43, for that last conversion in order to figure out how many sulfate ions are there. So we need to find the molar mass of the iron 3 sulfate. So do that calculation. You should get 399.91 grams. So working the problem, we'll start with the mass we're given. We have 1 gram of the iron 3 sulfate. The first thing we can do is use the molar mass. I can tell that because I'm starting in grams and the molar mass has the unit grams in it. So 1 mole of the iron 3 sulfate has the mass of 399.91 grams of iron 3 sulfate. The grams of iron 3 sulfate cancel. Now we can go to particles. And recall, iron sulfate would be ionic, so that means the particle would be a formula unit. So every mole of Fe2SO43 contains 6.022 times 10 to the 23rd formula units of that iron 3 sulfate. So moles cancel. Now the last conversion, just simply look at the formula. If I look at my formula here, I can see there are 3 sulfate ions in every formula unit. So that's my conversion. I put it down here at the bottom so it fit. So notice the formula units of Fe2SO43 will cancel. These one's in the numerator, one's in the denominator. And notice on top here I have 3 sulfate ions. So I'll simply multiply by 3 at the end there. You do all that, you should get 4.52 times 10 to the 21st sulfate ions, which you'll get there. All right, this concludes the 2-lesson series on molar mass. The big ideas here, remember, we use molar mass to convert between moles and mass. That's that last learning target. You still might have to use Avogadro's number, though. if you're being asked about particles. Anytime you're asked to find a number of atoms or molecules, or if you're given a number of particles and you're asked to find a mass, you have to use Avogadro's number. Really, really encourage you to use that flow chart that's been on some previous videos. I'd print that out, or maybe better yet, work on coming up with that yourself. That way, if you wanted to use it on your own, you could draw it out. I think that's very beneficial for you.